Good evening, everybody. Welcome to a wonderful evening of Chem 1105 with your host, me, Dr. White. And tonight I'll be reviewing for test 4. That's test 4. In case you forgot, on Blackboard, I have an announcement that I sent out on April 25th, and you also should have gotten an email that test 4 will be this Thursday, the 2nd of May. It's May already. Wow. Where's this year going? All right. Test 4, like I've done the other tests, 8 o'clock or earlier, probably earlier, on Thursday, the 2nd, I will send out an email with the password for the password protected PDF file for test 4 that you download from Blackboard. Now, test 4 will cover chapter 7, acids, bases, and the chapters dealing with organic chemistry. It has 17 problems on 9 pages, no multiple choice, but some questions are multiple part. And the breakdown are acid and bases, 56 points, organic chemistry, 49. So it adds up to 105. So there's five bonus points. You will need a scientific calculator. Now, the Monday this Sunday, 5 p.m. or earlier, I'll have your grades on Blackboard. And by Monday or earlier, sometime Sunday probably, I'll also email out to you individual emails with the points for each answer you did on test 4. And the next Monday at 8 p.m. in a Zoom meeting, I will go over the answers for test 4. Now, one other thing, don't forget, May 6th, I believe that's a Monday, let's check. Yep, May 6th is the deadline for the extra credit project. Remember, it's optional, but it's 10 points, which can only help you grade. And before it's due, and don't wait until last minute, but this week sometime, send me your chart or table, really table for the extra credit project, and I'll look at it. And if there's anything wrong, I'll get back to you how to fix it. That way, there's no reason anybody who spends a little time can do the extra credit project for 10 bonus points. All right, let's start with the review for test number 4. And this file is in the lecture section of Blackboard, cleverly named Chem 1105 Test 4 Review. And these are things you should know for test 4. But before I go into it, let me remind you that also in the lecture section of Blackboard, you'll see important information, test number 4. And these are things that this will be the last page of test 4. In the past, students have to memorize this. But a couple of years ago, I said, I should test people's knowledge of chemistry, not how good their memory is. So that's why this is the information I'll give you. Everything else you have to know on your own. All right, we started out test 4 review with acids and bases. And the first question is, what's a Bronsted-Lowry acid? And the easiest definition, it's a proton donor. A proton is H+, as you see in red. You could also say any substance that donates, gives up a proton to another substance. That's an acid. You should also know what is a Bronsted-Lowry base. And that's a proton acceptor. Oh, you got a proton? Give it to me because I'm a Bronsted-Lowry base. Excuse me. That's any substance that can accept a proton from another substance. So you should know an acid is a proton donor and a base is a proton acceptor. Now, you should also be familiar with the chemical formulas of key acids and bases. I'm not going to ask you to learn their names, but you should know the HCl, hydrochloric acid, it's an acid, H2SO4, sulfuric acid, that's why it's called an acid, because it's an acid, and HNO3, nitric acid. These three are acids. There are a lot of other acids, but these are some of the most well-known acids in chemistry. Now, remember, an acid is a proton donor. Now, not all, but most acids start with H. Not all, but most acids start with the hydrogen. All right, now bases, you should know NaOH, sodium hydroxide is a base. NaOH, sodium hydroxide is a base. KOH, potassium hydroxide is a base. And finally, NH3, ammonia is a base. Now, I won't ask a specific question in terms of what is the dissociation of water, but you should be familiar that water can react with itself. That's what this shows here. And it's an equilibrium, means it can go both ways. I like the special effects. Don't answer that question. And it can form a small amount. This is called H3O plus, the hydronium ion, and OH minus is the hydroxide ion. Now, there's the equilibrium constant, but because it's water, it's called Kw. I wish it was named after me. Maybe I was destined to be a chemist because they named something with my initials, Kw. Kenneth White, yay. And that's the ionization constant for water. And you should be familiar with that the brackets here mean concentration, moles per liter. And this is the concentration of the hydronium ion times the concentration of hydroxyl. And this should be 1.0 times 10 to the minus 14. And this is at room temperature, 25 degrees C. You go colder or warmer, it changes. But for most, like everything in our life, you can use this. And this is given to you an important information. Now, when we talk about acids and bases in aqueous solutions, there are three terms you should be familiar with. Acidic solution. And you should know an acidic solution is a solution in which the hydronium ion concentration is greater than the hydroxide. While I get my pad oriented right. So acidic solution, the hydronium ion concentration is greater than the hydroxide. Now, the opposite of that is a basic solution. And that's where the hydroxide concentration, solution in which the concentration of OH minus ions, hydroxide, is greater than the hydronium ion concentration, H3O plus. And this is called a basic and sometimes called an alkaline solution or alkaline solution. I've heard it pronounced both ways. And if you have alkaline batteries, the material in there is basic solution. Now, a neutral solution is a solution in which the hydroxide concentration is equal to the hydroxide concentration. So let's review. I say I have an acidic solution. I know the hydronium ion concentration is greater than the hydroxide. I have a basic solution. The hydroxide concentration is greater than hydronium. And finally, if I have a neutral solution, hydronium ion H3O plus is equal to hydroxide OH minus concentration. Now, if you were looking at these like 1.0 times 10 to the minus 11th and 1.0 times 10 to the minus 10th, which is larger, which is smaller, that's not easy. So someone came up with the pH concept. And what it is a small scale of numbers that's used to specify molar hydronium ion concentration in an aqueous solution. And it's defined pH equals minus the log of the hydronium ion concentration. Now, if the hydronium ion concentration is 1.0 times 10 to the minus x, this right here is this, then the pH is x. On a test, I'll always have some number times 10 to the 1.0 times 10 to the minus x. So that's my gift to you. Shh, don't tell anybody I'm being nice. Remember that. Shh. You don't have to learn, even though Dr. White knows how to do logarithms on a calculator, because I'm going to always give you this to make your life easier. Now, this is the pH. How does it help us tell if we have an acidic, basic, or neutral solution? And probably the most useful, important thing I will teach you this semester is the pH scale. It's time for Dr. White to be subtle. See, I can be subtle. Know this. And what the pH scale is a scale that goes from 0 to 14. And when you're at pH 7, the solution is neutral. When you're below 7, you have an acidic solution. And when you have above 7, it's a basic solution. And if you were to test something like ketchup, which is made with vinegar, that's made with acetic acid in the vinegar, it's got a pH about 2 to 3, which means your ketchup is acidic. If you look at what would be something basic, certain drain cleaners that use sodium hydroxide, the pH would be about 13, which means it's basic. So at pH 7, neutral pH, below 7, acidic, above 7, basic. Notice it says important, and I was subtle on top. Hint, know this. Now, let's try a couple of things with pH. Hang in there. So question is, if the pH, and I could have set up a solution, or no, if the hydronium ion concentration is 1.0 times 10 to the minus fourth of a solution, then what is the pH of the solution? And is it acidic, basic, or neutral? Well, what are we trying to find initially? pH. What are we given? The hydronium ion concentration, 1.0 times 10 to the minus fourth. Hold on, let me fix up that a little. That looks better. So how do we proceed? Well, in case you forgot, you can go to important information. pH is minus log of the hydronium ion concentration, H3O plus. If H3O plus is 1.0 times 10 to the minus X, the pH is X. So we know this. And this number right here, we have here, and when that number is 1.0 times 10 to the minus X, which in this case, X is 4, we know the pH is equal to X. In this case, X is 4. So the answer, first of all, the pH of this solution is 4. And the next question is it acidic, basic, or neutral? And you should know, hint, this. And notice the pH is 4. When the pH is below 7, it's acidic. When it's equal to 7, it's neutral. And when it's above 7, it's basic. So therefore, if the pH is 4, it's below 7. So this is acidic. And by the way, I'll do it again. Be real subtle. You should know that pH chart. If anything, you leave my class, this is one of those things you should always know. It's quite helpful. All right, let's do one more. All right, question is, if the hydroxide ion concentration, OH minus, is 1.0 times 10 to the minus 2, then what is the pH of the solution And is it acidic, basic, or neutral? So what are we trying to find? Once again, pH. What are we given? And that's what we have. But if you look at important information, test number 4, you know, pH equal minus the log of the hydronium ion concentration. Uh-oh, this is not the hydronium ion concentration. What do we do? Well, if you look at important information, test number 4, you see this. Hydronium times hydroxide equals 1. That should be 1.0 times 10 to the minus 14. And you can use that and the hydroxide concentration to determine the hydronium concentration and then determine the pH. So you need 2 steps. So the first one you have to find or determine the hydronium ion concentration. So we know this from Kw, the ionization constant of water. Now we want to get this alone on one side, because we want to find first H3O plus. Well, how do we get rid of OH? Well, anything divided by itself is the number 1, and 1 times anything is that thing. So you've gotten rid of it. So I'll divide this side by hydronium ion concentration. Whatever you do to one side, you have to do to the other. So I'll divide the other side by the hydronium ion concentration. That's OH minus. This divided by this is the number 1. Remember, A divided by A equals 1. 1 times the hydronium is that. And that's equal to 1.0 times 10 to the minus 14 divided by the hydroxide ion concentration. And we'll put this number in, which we have here. And I can do this in my head, but if you need your calculator, you'll find the answer is that. Are we done? No, we're trying to find the pH. We now have the hydronium ion concentration. And now we'll do the second step. Determine the pH. And again, from important information, test number 4, pH equal minus the log of the hydronium ion concentration. We just calculated it right up here, so I'll put it in. And when its pH is equal to 1.0, log of 1.0 times 10 to the minus x, the pH is x, and therefore this is 12. So we have the pH now, And the question is it acidic, basic, or neutral? And again, you should know this chart. At 7, you have a neutral pH or solution. Below 7, it's acidic. And above 7, it's basic. And hopefully you all know 12 is greater or above 7. So this is basic. All right, next I talked about buffers. And buffers are a mixture of two chemicals, or it's a solution that resists major changes in pH when a small amount of acid or base is added. And your blood is buffered because it's important to keep it very close to 7. Otherwise, you would die. And therefore, if I add a small amount of a dilute solution of acid or base to a solution or water, guess what? Or to a buffer solution, not water, guess what? The pH stays the same. Now, if I add an acid to water, that will make it more, that will cause the pH to go down and it'll make it acidic. The pH will go down when you add an acid to water. When you add base to water, the pH will go up. By the way, while we're looking at the word acidic, I talked about in one of the lectures that years ago, pollution from power plants that use coal, especially in the Northeast, polluted the sky, the air, and that formed in certain places in the clouds sulfuric acid. And when it rained, it came down into water in the rain, and they called it acid rain or acidic rain because it was, and it destroyed plant life and also natural stuff in rivers, aquatic life, and animal life in the forest and killed trees. Yeah. Luckily, we cut that due to the EPA cracking down on power plants. That's mostly gone away. Now, an important thing is the titration. When you add an acid to a base, HA is acid, V is base, there's a reaction, proton transfer, you get a salt. And this is a neutralization reaction, because if you add an acid and you add a base, the pH at a certain point will go to 7, neutral pH. Now, you should know when you add a mixture of a known acid and a certain amount with a known base at neutralization, when you're at pH 7, moles of acid equals moles of base. Now, I simplified the math to give you this equation: milliliters of acid times molarity of acid equals milliliters of base times molarity of base. Hold on. I have to sign in to the Adobe Cloud. I don't know how I got signed off, but now we're up and running. Hopefully you've all looked at the practice problems. Some I've done tonight. All right, let's look at number 12. If you have to add 1.35 times 10 to the third ml is milliliters, that's volume of a 1.53 capital M NaOH. Remember, M is molarity, moles per 1,000 milliliters. And the key thing here is to neutralize 1.87 times 10 to the minus 2 milliliters of an aqueous HCl, hydrochloric acid solution. What is the molarity of the HCl solution? Before I do this, you saw the word neutralize. At neutralization, this is important information. Test number 4. I gotta get this finger fixed. Anyways, the moles of acid equals moles of base. And then, you know, milliliters of acid times molarity of acid is equals milliliters of base times molarity of base. By the way, this is for a monoprotic acid and bases. That's a base or acid that can only accept or transfer one proton. If you have diprotic, it's different equation you have to use, but we won't do that in this class. So we're trying to find the molarity of HCl. We're given the volume of the NaOH and its molarity. We're given the volume of the HCl solution. At neutralization, moles of base equal moles of acid. And this is milliliters of acid times molarity of, let me back up. That's what it sounds like when you back up a tape. None of you have ever probably seen a tape recorder. Never mind. Anyways, milliliters of base times molarity of base equals milliliters of acid times molarity of acid. That was important information. Now, if we put in the numbers, here's the milliliters of base, here's the molarity of the base, here's the milliliters of acid. And we're trying to find the molarity of acid. How do we get that alone on one side? Well, we've got to get rid of this number, 1.87 times 10 to the minus, or 10 to the squared milliliters. So if I divide by it, anything divided by itself is number 1, and it's gone. But whatever I do to one side, I do to the other. Now, I'm going to rewrite this. So this would be molarity equals this right here. Notice milliliters cancel out. You're left with molarity. And don't forget, use proper significant figures for all calculated answers in a multiplication division. You get the same number of significant figures in your answer as the number with the fewest significant figures. This is 3, this is 3, this is 3, this is 3. Now, you could have also written this 1.10 times 10 to the 1. Same thing. All right, let's talk about organic chemistry. And organic chemistry was started with the investigation of molecules that came from things that were alive, like plants, animals, and us. Now, the most important element in organic chemistry is carbon. And the carbon atom has 4 valence electrons. And what you should know is there's always four, 4 bonds to carbon. I can do it with my eyes closed. 4 bonds to carbon. You should know that. And carbon can bond to itself and other elements. And when it forms to itself, it can form what we call chains with branches, and it can form rings. Now, you should know, what is a hydrocarbon? It's a molecule with only carbon and hydrogen atoms. You should know there are 2 types of hydrocarbons. Saturated hydrocarbons, since it's a hydrocarbon, it's a molecule with only carbon and hydrogen atoms because it's saturated, in which all carbon-carbon bonds are single bonds. Now, unsaturated hydrocarbons are molecules with, it's a hydrocarbon, with carbon and hydrogen atoms. But because it's unsaturated, it has at least one or more carbon-carbon multiple bond called a double bond and a triple bond. By the way, Mother Nature never did triple bonds, but she did a lot of double bonds and single bonds. Now, when we learn organic chemistry, the important thing here is functional groups. And a functional group is a group of atoms together in a molecule that gives similar functionality and properties to molecules they're in. And how do you find a functional group? You look and you should know this. You should know how to find a functional group. Look for anything that is not a carbon atom or a hydrogen atom or carbon-carbon single bond, and you've found a functional group. If you look at the organic chemistry practice problems, circle the functional groups, 2 points each maybe. You notice an oxygen with 2 carbons, that's called ether. You don't have to know the names. You take my Chem 1212 here or Chem 170 at Elgin Community College, you will have to know the names because that's organic chemistry 1 semester. And here we have carbon oxygen, double bonded, and this is a functional group. It's called an aldehyde. Here, oxygen with a hydrogen and a carbon, that's an alcohol. And you can see other examples here. So look for what's different. What's not a carbon-carbon single bond or a carbon or hydrogen atom should get your attention like that. That's better. Or even like that. All right, how to draw organic molecules. And we use what's called condensed structure. I'm not going to do anything with condensed structure with parentheses. Remember, there's always 4 bonds to carbon. And bonds are shown by lines, not like in Lewis structures with dots. And you should know how to put in hydrogens in a molecule. And if I were to ask you, put in the hydrogens, and there's a problem like that in the problem set, this first carbon has one bond to it. There's always four bonds to carbon. 4 minus 1 is 3. So that means this should have 3 hydrogens. This carbon now has 1, 2, 3 bonds to it. There's always 4 bonds to carbon. 4 minus 3 equals 1. So this has a hydrogen. This carbon has 1 bond to it. 4 minus 1 is 3, so 3 hydrogens. This carbon has 1 bond to it already. 4 minus 3 is 1. And we're left with one more to go. And that's this carbon. It's got 1, 2 bonds to it, to the carbons. But there's always 4 bonds to carbon. 4 minus 2. Oops, I've got ahead of myself there. I was going to write a hydrogen. Is 2. Therefore, this has 2 hydrogens. And that you should know. Now, one area that's very important, especially like in your hormones, are cycloalkanes, and we call those rings. And they're represented by polygons, many gon-sided things. And remember, each bend in a line is a carbon atom. And if I do totally line draw method, each end of a line is a carbon atom, and each intersection of a line is a carbon atom. Hydrogens are not shown on cycloalkanes, otherwise known as rings. And if we look at, say, B, how many carbons are in the following molecule? If we look at B, here we have a ring, and you count each bend in a line. 1, 2, 3, 4, 5, 6. Outside the ring, we have 7, 8, 9, 10, and down here 2 more, 11, 12, and that's got 12 carbon atoms. If we look at C, we have a ring with 5 carbons, 1, 2, 3, 4, 5, and outside the ring, 6, 7, and 3 more, 1, 2, 3, make 10. And that's the skill you should have. Now, in organic chemistry, we study what's called general reactions. And this is where certain groups of organic molecules always react the same way. And most of the time, by the way, organic chemists are really lazy. We don't balance equations. And one example is saturated hydrocarbon, oxygen. This is called combustion. And I don't have here, but you got to need a little heat source like a spark. You get carbon dioxide, water, and heat. And you should know that. Another one is called hydrogenation, which is an important area. And I did a lot of research when I was in industry using hydrogenation. And I came up with molecules that I used hydrogenation to make. And my first US patent, I used hydrogenation to make a new molecules. All right, now this is a depiction. R is like X and Y in math. Anything with carbons is what this says is if you have a molecule with a double bond, and react it with hydrogen and catalyst, And here are your different catalysts. Say nickel, you break one of the bonds, and each carbon of the double bond gets a hydrogen. Now, an important concept in organic chemistry, 99.99% of the time, you never break carbon-carbon single bonds. No, you don't. So if I were to have this reaction on test 4, and I say give the organic product or products, notice I have 3 carbons here. Look for what's different. A double bond. I'm reacting with hydrogen, and platinum is the catalyst. That could be platinum, palladium, or nickel. And you break one of the bonds, and each carbon of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? No, so I won't. So I start with 3 carbons. I end up with 3 carbons. Here are my 2 carbons of a double bond. I only have a single bond now. Each one gets a hydrogen. I know there are 4 bonds to carbon. This has 1. 4 minus 1 is 3. This carbon center has a hydrogen, 1 bond, and 2 bonds to carbon. So again, 4 minus, or I should say 4 minus 3 is 1. And here, this last one has a hydrogen, a carbon. 4 minus 2, because there's always 4 bonds to carbon. Now you could add this and write it this way. This comes up with here like that. This is still, and either way would be correct on a test, which means you should know how to do this. All right, now areas I've worked in the chemical industry, fats and oils, and you should know a fat is a triglyceride that's a solid or semi-solid at room temperature. An oil is a triglyceride that's a liquid at room temperature, like olive oil is a liquid at room temperature. Now, there are different types of fats and oils, and I worked with these. I worked at a company where we purchased every week about 2 to 3 million pounds every week of tallow, which is beef fat, or yellow or white grease, which is pig's fat, and you should know that. Now, if you take organic chemistry, you'll learn about surfactants, and an important surfactant is soap. And you should know how does soap work. And the first thing, soap has a hydrocarbon tail, also known as nonpolar, and a polar head. And you should know this. And the important piece of the puzzle is like dissolves like. And you should know water's polar, dirt and grease are nonpolar. And what happens is you form micelles when you wash your hands with soap and water, because you just do water, they'd still be dirty. Notice I use soap and water, so that's why my hands are clean. And you form micelles, and you should know this. And let me go through a better version of how to learn this. Leaving my class, you should know Next time you wash your hands, your hair, your dishes, your clothes, this all works the same way. You should know that soap non-polar tail, polar head. You should know water is polar, the most polar substance on our universe. And dirt and grease are non-polar. I tell you, I was always the first one down a spelling bee, not L-O, it's L-A, polar. And the important part of this puzzle, how soap works. Now let's try it. Is like, dissolves like. This is the key, how soap works, and you should know that. And you should know that dirt, if we had a small piece of dirt, let's try this again. Dirt is nonpolar, and the nonpolar tail of soap molecules is attracted to it. Now I'm just going to show a couple, but it totally surrounds the dirt, and you should know this is called the micelle. And the micelle has the polar heads all outside surrounding the dirt. So the micelle looks polar to water. We all know H2O is water. And the micelle looks polar to water. And water says, well, like dissolves like. Micelle, you're polar, I'm polar. Let's go down the drain together. And they do. And that's how you get your hands clean. Anything else, you use soap or laundry detergent, which is a surfactant type of soap, and your dishwasher, the soap you put in, or the liquid soap you do when you do it by hand, and it all works the same way. And time to be subtle and know this. And one final thing I'd like to discuss tonight is how does a towel work, or a paper towel? Now, cotton has these structures, and the OH groups on the carbon, OH, they're called hydroxyl, are polar, and they attract water. How? By hydrogen bonding. And that's how a towel works. It's not magic, it's organic chemistry. And remember, you should know, how does a towel work? And it works by hydrogen bonding to the water. And with that, let me remind you, hand in your labs. Also, let me remind you, the due date is Monday, May 6th for the optional extra credit project. And well before May 6th, you want to make sure you get 10 bonus points. Email me your project well before it's due. I'll check it. And if there's things wrong, I'll let you know and I'll help you fix it. So with that, I'm done for tonight. Remember this Thursday, test number 2, May 2nd. I'll send out the password at 8 p.m., 8 a.m. or earlier, probably earlier. And it's due by 8 p.m. Friday, May 3rd. And with that, I'm done for today. And I'll say in Yiddish, meaning go in hell, gay and gesund. And what I stole from Granny and the Beverly Hillbillies. Bye now.